Okay, hello. I think it's time to start. Do you hear me?
Can you say one word more?
Microphone was up.
Yes.
Right now the quality should be much better, I hope. Okay, so we are starting our fiber part of this lecture. So today I will present you some very basics.
Sorry, but you're muted. Like you moved your chair and sound stopped.
Still, we can't hear you.
Mute button was. Right now it should be okay.
Yeah, now we can hear you.
Okay, so don't hesitate to just break if I'm telling something you don't understand, and also be prepared for the questions. I will ask you questions during the lecture, so it would be nice if somebody of you at least would try to answer the questions. Yeah, I think it is the best way to give a lecture, to have some interaction with the students. So don't be afraid that there is no wrong answers here. Exactly the same like on the laboratory. You know me already, so you know you don't need to be afraid of questions and of answering. Even not proper answers are okay for today and for whole the lectures here. Of course, not for the final test we will have after the semester. Starting the lecture, I need to switch and I need to just show you the screen, the proper one. Are you able to see the first slide of my presentation? The title one?
Yes, you can.
Okay, so we can start. Here you have my data. I'm in the room where I'm sitting right now, and email. So in the case you want to contact me, you can contact me by an email, and of course on the laboratory. So as I told you, we will speak about the optical fibers. So the first and the most important thing to start is why the optical fibers were developed. How do you think? Do you have some ideas why they are developed all the time, and we need to learn and speak about the fibers? You have no idea.
Main telecommunication medium right now, and with very high throughput, bandwidth, etc.
Yeah, and in fact, this was the main reason why they start to develop optical fibers. Exactly the things you mentioned. I mean, for transferring the information through some channel, we need to have some media to transfer this information. And optical waves, you know, the optical waves has extremely high frequencies, so they have huge capacity for channels and for the information. So the optical communication can be very extremely fast, in fact. And in our times right now, I don't think any other transmission media is able to transfer such a high information rates we are using today. I mean, these videos, in all the internet, all the things which are transferred to the network, all of them requires huge bandwidth to transfer, yeah, and only optical signals are able to transfer such amount of the informations. So I hope you heard about some advantages about the fibers, the huge capacity we mentioned already, but others. What do you think about the advantages of the fibers versus standard cables using electrical signals?
I don't know if it was mentioned, but smaller attenuation over long distances.
Yeah, small attenuation. Of course, the modern fibers fits to this property, yeah, and this is good point. So we can transmit the information at huge distance using the fibers. What else? Yeah, it is also quite huge advantage of the fibers versus standard cables. I mean, electrical signals transferring cables.
They're not conductive to the current or voltage.
Yeah, it is also advantage, especially if we want to use some transmission in, let's say, high voltages environment or something like that. Yeah, sometimes we want to have some media not conducting current to avoid the problems, the inductance of high currents in our transmission media and other things. Any other advantages you can imagine or mention?
Low footprint, they are quite thin.
Yeah, small size, quite important thing, but in fact, regarding, let's say, typical use, the fibers are pretty small, but the fiber cables aren't. So it is advantage, but not so important, in fact. Okay, so let's check. I just prepared most of them. As you can see, almost all of them was already mentioned by you. High information capacity, yeah, small losses, immunity to interferences, almost the same. They do not interfere with other signals. Dielectric also was mentioned. Low weight, it is quite similar to small size, but also high reliability. And nobody just tell about this one, hard to wiretap. Sometimes it is told that signal in the fiber cannot be wiretap, but in real life you can wiretap a fiber. It is enough to bend a fiber and some of the light goes outside from the fiber. But if you want to wiretap the signal from the fiber, it means also you are decreasing the power which goes to the receiver. So the receiver can see something's wrong going on with the signal. So the signal level became smaller. So it is quite easy to localize the place and the fact that somebody just tried to wiretap a signal from the fiber. Yeah. So as you can see, you are quite well in guessing, or maybe you already know about the disadvantages of the optical fibers. So we can go to the next part and to start to explain you how we can make such a media to transfer the optical signals at huge distances, which as low attenuation as possible. Yeah. So we can imagine at the first approach, almost everybody who wants to develop the fiber, something which is able to transmit the light, some kind of a tube. Yeah, we can imagine tube. We can cover this inner wall of a tube with some reflective layer. And at the first approach, it looks like it could be okay just to put the light inside such a tube and transmit the light at some distance. But the numbers will show you in a moment that this approach is not so good. In fact, regarding this transmission at long distance, this approach is impossible to realize. You can take extremely good quality reflective layer of 99% of the reflection. Do you know what order of reflection do you have in your, let's say, bathroom mirror? How many light is reflected back from such a layer you have in your bathroom? Do you know what order of this reflection? How many percent of the light is reflected? Of course, you can guess. 90%, do you think, is reflected from standard, let's say, bathroom mirror, or less? 80?
Like something
I'd say
around
around
50%.
Slightly higher, something about 60%. 60% of the light is reflected and 40 is wasted. Yeah, so you can imagine 99% of the reflection, it is extremely good quality of the mirror. Yeah, so if we have such a good reflection, look, transferring the light through such a tube, after 10 reflections we'll have 90% of the input power, but after 1000 reflections we'll have only very small amount of the light put to the input. And you can imagine 1000 reflections, if our tube is small, can be reached after a couple meters of a transmission. So it also means at kilometer of a distance the attenuation will be extreme. Yeah? So this approach cannot be used for making optical wires, optical fibers. We need to find another solution, and this solution is some physical phenomena called total internal reflection. This phenomena gives us 100% of reflection every time. Yeah, and right now I will show you how we can go to this one and what are the conditions needed to be fulfilled to have such a phenomena and to use it as a phenomena which allows us to make this optical fiber. So we are starting from well-known phenomena like light refraction. Everybody knows what is the light refraction. This is in the case where the light travels from one media into another media. These two media has different refractive indexes. Yeah, so this is the basis. So I just prepared some demonstration how it is operating. We have some prism, laser beam going from your left. I hope from your left. There is no mirror applied to this picture. Yeah, this prism is made of glass, and there you can see this internal ray inside of this prism. And of course, the law of refraction operates at the angles of incident and refraction. I will show you on the next slide the equations for this one. Yeah, but right now we can just see how these angles are changing. Excuse me, not this key. I want to just erase all the. Yeah, you can see changing the angle of this surface, this border between the air and the glass. We are changing the angles also, but we are going from the air to the glass. The air has a refractive index something close to 1. In first estimation, it could be taken as an 1. and the refractive index of the glass is this is special glass designed for high chromatic dispersion, because this is prism taken from some monochromate or so. So the refractive index of this glass is pretty high, 1.8 or something like that. Yeah, so you can see the input angle is bigger than this refracted angle. Yeah, and speaking about the refractive index, some of you already just met with this my question. What is the physical meaning of refractive index? What does it mean the refractive index is equal to 1 or equal to 1.8? Some of you should just remember the laboratory, especially the groups who made this electro-optical modulator exercise.
So it's like directly mapped on the velocity of the propagation of the light inside of the media.
Exactly, versus the velocity in the vacuum. Yeah. So 1 means the velocity, the speed of the light in the vacuum. 1.8 means in this glass, the light beam travels 1.8 times slower than in the vacuum. This is the physical meaning of the refractive index. It is quite important regarding next part of this lecture. I will show you some special type of a fiber. So, and also it is good time to just remind you about this thing. I mean, this physical meaning of the refractive index. And finally, this light refraction is given by so-called Snell law. As you can see, the relation between the incident angle and refracted angle, alpha and beta, is pretty simple, because it is only connected with the refractive indexes of the media. Yeah, and some basic calculation for the case where incident angle is 45 degrees. Yeah, and light goes from air into water. So after passing this border between these two medias, we will have this beta angle equal very close to 30 degrees. Yeah, so it is just example showing you what are the relations between the angles. Of course, there is also opposite situation possible. I mean, if the refractive index of the first media is higher than the second one. Yeah, and in such a case, other relations appears. The incident angle is smaller than refracted angle, and we can ask what will happen if we just increase the angle of incidence to have angle of refraction equal to 90 degrees. What will happen in such a way? You have the answer already on the screen. Yeah, it should behave like reflector. So all the beams should be reflected in such condition. So let's see how it is working in, let's say, real life. Once again, exactly the same prism. I just put blue laser in that case from the left side. It goes to our prism. Of course, here it is refracted, but the angle dependence you can see is we are going from 1 to 1 point something. So this incident angle is higher than refracted angle, but at the second surface where the light goes outside the prism, we have opposite situation. Yeah, this angle is smaller than refracted angle. So what will happen if we just increase this angle, this incident angle? I will increase this angle. We have normal, and we will increase this angle to higher value. And please observe what's happening with this output beam going out from our prism. Yeah, and this was the moment you should try to catch. And of course, the move in opposite direction. Yeah. So you can see what's happening if we are closing. Oh, it doesn't refresh. So right now we are very, very close to this critical angle. And right now it is, of course, exceeded. So you can see the behavior. What's happening if we are closing? Yeah, right now it is exactly on the critical angle. Yeah, so this refracted angle you saw, it should go in this direction. Instead of this, it is just reflected here, and you can see by the intensity of these two beams, they are exactly the same from both sides. Yeah, this incident and reflected beam is exactly the same intensity. So in ideal conditions, we'll have 100% of the light just reflected on such a border, such a construction where we are trying to extract the light from the higher refractive index media into the lower. Okay, so we can go to the next slide, and here you can just see how you can calculate this critical angle. Yeah, so angle which guarantees you 100% of the refraction, you should just put to this Snell law two angles. First one, this is the incident angle, and as a refracted angle, it should be taken this 90 degrees angle. And this angle, this critical angle, is just a simple arcus sinus function of this refractive index's quotient. Yeah. So this is how we can just calculate this critical angle. It means that every incident angle higher than this critical angle will give you total internal reflection. So 100% of the reflection. If this incident angle is smaller than this critical angle, of course, we'll have some refraction. So the light will go inside this second media. Yeah. So this is the condition we need to fulfill to have total internal reflection. You can see it is quite easy to fulfill, especially when we have some high incident angles. And also, looking at the equation showing you this critical angle, one should already know why refractive index of the first media should be higher than the second one. Yeah. This should be less than 1 to have any mathematical sense. If N2 is higher than N1, under arcus sinus we'll have something which is higher than 1. It means it doesn't have any sense regarding the mathematics. So you cannot calculate any angle in such a case. Yeah, so this total internal reflection cannot be fulfilled. And since we know what we want to have and what we should do to have such a phenomenon like total internal reflection, giving us this 100% of the reflection, we can construct some wire using this phenomena to just simply guide a light. And on this picture, you can see very typical construction of the optical fiber. This is so-called cylindrical fiber. As I told you, very, very typical geometry of the optical fibers, quite easy to fabricate, for example, and to use, and also it has quite nice properties regarding transmission of the light beam. Later on, I will show you, not on today's lecture, but on one of the next lectures, I will show you also different geometries of the fibers, and I will say a couple words about the propagation of the light in such structures, but right now we will just simply focus on these cylindrical fibers. Of course, this inner layer should have refractive index higher than this external layer. This internal layer, it is so-called core of a fiber, and external layer, it is so-called cladding of a fiber. Yeah, and of course, both of them, unfortunately, need to have perfect optical quality. I mean, they should not attenuate a light, for example, and also they should be perfectly transparent, not blurry and other things. Even cladding should be with the good or very good optical quality. Yeah, this is why we cannot match, for example, the fiber which is made only of core surrounded by the air. Because if you just simply touch a fiber in this point, you will introduce quite high attenuation on such a place, because speaking about this total internal reflection, yeah, so we have these two rays. Of course, in ray geometry, we don't have any light in this second layer, but in reality, there is such a we need to just treat the light as a wave, and this wave, very small amount of this wave appears in this second layer also in so-called evanescence field. Yeah, so close to this border, we have quite high intensity of the light, and it is decreasing with the distance. So it means if we just put something which is attenuating in this place, we are attenuating the beam which is reflected from such a structure. So it is why this cladding of the optical fiber also needs to be done with the high optical quality material, and it is quite important. Okay, so next demonstration, I just used some, let's say, plexiglass bar, and put the laser beam from the left to this structure and change the angles, so you will see how the light is propagating in such a structure using this total internal reflection. Unfortunately, these input and output beams aren't visible, but you can easily see the propagation of the light inside of this plexiglass. The quality of the surfaces here wasn't so good, so this is why this ray here isn't perfect quality, like I just showed you, showing this prism. It has quite good quality of the surfaces. This one has quite poor quality of the surfaces, but even though you can easily see how the light is propagating through such a structure, and the picture showing you exactly the same, but you can imagine what will happen if we have the beam which is propagating close to this critical angle. Yeah, so what will happen if we are propagating the rays which are close to this threshold, this critical angle? So next movie will show you right now the same plexiglass bar, but I just put it in some cuvette with water, just to show you input beam and output beam to be clearly visible. Yeah, and of course I will change the angle, of course, between this input beam and our, let's say, artificial fiber. Not this key. As you can see, we have one internal reflection. Yeah, I'm increasing the angle. Two internal reflections. I'm still increasing the angle. Third one. Yeah, so we have right now beam going to the fiber at some angle. Of course, it is propagating in this bar and reflecting from each surfaces. But we are also increasing this angle all the time, yeah? Increasing this angle will make more and more reflection at some certain distance. But look carefully right now what will happen in a moment. Excuse me. So we need to go once again to this certain moment. Second, third reflection, and yeah, look, right now, I just exit this critical angle here. So you can see some part of the light start to leak out from our fiber on this reflection and this one. And of course, this one also, yeah. This angle here is pretty close to 90 degrees. So it means we are almost exactly on this critical angle here. Of course, I just increase the angle even more. So you can, right now you can see what will happen if we just put the light to our fiber with the incident angle higher than certain critical value. After 2 reflections, we have no light inside the fiber at all right now. Yeah, you can see it quite easily. First reflection, second one, and here we should have another rays, but they aren't visible because almost 100% of the light goes outside our fiber after only 2 reflections. Yeah, so this is, you can imagine how sharp this dependence is. Observing the situation once again, yeah, we have 100% reflection, and going back right now, we have much smaller than 100% reflection. So you can imagine we cannot put a light into the fiber at every angle we want to, but there is some range of the angles possible to be transmitted through the fiber. Yeah. It is connected with so-called acceptance angle of the fiber, or sinus of this angle is called numerical aperture. NA, this is extremely important parameter of a fiber, this numerical aperture, telling us what is the maximum angle we can use to launch the light into the fiber to be guided. If we just put another ray with the higher angle inside of the fiber, we wouldn't have this total internal reflection, but the light will go outside the fiber after a couple reflections. You saw 2 of them are quite enough to have almost nothing in the fiber left. Yeah, and as you can see, the equation for this numerical aperture is pretty simple, in fact, because it is dependent only on the core refractive index and cladding refractive index. Square root of squares of core and cladding refractive indexes, difference between them, in fact. Yeah, so quite simple formula to give this refractive this numerical aperture. And right now I can also try to ask you, how do you think why I just put this my artificial fiber into the water? I must put it to show you this critical angle, in fact. The visibility of the input and output rays, I told you already that it was also the reason, but it wasn't the main reason I just put this fiber into the water. Do you have any idea?
So it should be connected with the refractive index, I suppose.
Yes, in the air, of course, cladding refractive index will be something close to 1. You can take it as a 1. And the core refractive index, it was plexiglass, so the refractive index of such a material is something 1.45. So if you just simply put these two values into this formula, here we'll have something like 2.1 minus 1. So it will give us square root of 1.1. And of course, after the calculation, sinus of alpha should be equal to 1.1. Impossible, yes? It means for construction with the plexiglass and the air as a cladding, this acceptance angle was equal to 90 degrees or even more. Yeah, of course, more cannot be realized technically, but in fact, for such a construction, there is no chance to show you this acceptance angle, because for every incident angle, the light will be guided in such a structure. Decreasing the difference between the core and the cladding allows me to just show you this phenomena and to show you with relatively small angles. Yeah. Because it was visible even for the small angle, relatively, of course, small angle. Yeah. It is something close to 30 degrees or something like that. If this bar was in the air, I could even put the light input beam as with such a high angle, and it will be guided all the time. Of course, after refraction, it will be guided at some higher angle, but it won't work at all, at least regarding this demonstration. Yeah, so this is the main reason why I just put this plexiglass into the water. Okay, so very typical construction of the fiber. I told you, I mean cylindrical fiber. Regarding the refractive index profile of such a structure, it is called step index fiber. Step index because between the core and the cladding, we have some step in refractive index. Yeah, so this is the refractive index profile. Typical core diameter for such a fibers are 50 microns or 62.5 microns. These are typical core diameters for telecommunication fibers. Of course, you can make different core diameters for different applications, but regarding the telecommunication, these two diameters are typical ones. Yeah, and this is the first type of a fiber. Not so good, because I will show you in a moment what is the main disadvantage of such a fiber. Regarding the beams which are propagating, the rays which are propagating in such a fibers, you can see a lot of them, and all of them are traveling with different paths. Yeah, so for example, the ray which is traveling exactly on the axis of the fiber has much smaller distance to travel than the ray which is propagating with some reflections. In such a structure, also such a modes are possible. I mean, such a rays can propagate. So the ray can be just sliding on this border between the core and the cladding. These are so-called skew rays. All these rays, of course, they are propagating simultaneously. Yeah. Because we cannot introduce only one certain ray into the fiber and propagate only the one ray. And of course, since they have different optical paths in such a fiber, they will have also different time of a propagation through such a fiber. Yeah, minimum time will be given by this straight ray ray which is traveling along the axis of the fiber, and the maximum time will be given by the ray which are propagating close to this critical angle. So this is why we have this N1 and N2 appearing in the formula for this Tmax. Of course, time of propagation will be also dependent on the length of the fiber and the velocity of this, I mean the speed of the light. So as a result, if we just put some pulse signal into our fiber, yeah, on the output, this pulse will be longer because some energy of the pulse is propagating in this, let's say, fast modes, yeah, so they will appear first, and this part of this excited rays which are propagating with this many reflections inside the fiber will appear after longer time. So as a result, we'll have different propagation time for different, let's say, portions of our pulse, and it just simply leads to broadening the pulse. Yeah, on the input the pulse can be narrow, but on the output the pulse will be longer. This difference in the propagating time can be quite significant for standard fiber with these dimensions I told you. And typical broadening of the pulse for such a standard fiber is 20 nanoseconds per kilometer. 20 nanoseconds per kilometer, it means even if we just put the pulse, very short pulse on the input of our fiber, after 1 kilometer of the propagation, we'll have pulse which has duration of 20 nanoseconds. I told you nanometers, nanoseconds. I'm thinking about the time and speaking about the wavelength. At 20 nanoseconds per kilometer, this is this broadening of the pulse for such a standard optical fiber. And you can imagine, if we want to transfer the information through the fiber, we want to, for example, put some zeros and ones on the input of our fiber, yeah? 1, 0, 1, 0. So after 1 kilometer of a fiber, our ones will be broadened by 20 nanoseconds. And of course, zeros also, but they will overlap in such a way. So it means if the time between the pulses will be equal or higher than 20 nanoseconds, we will have zero modulation at all. Yeah, so we will lose all the information. Of course, if the time between the pulses, between the ones and zeros will be, for example, 40 nanoseconds, so it will be enough to be transmitted. Maybe I will draw you. Yeah, we have input signal looking like that, and time will be, let's say, 40 nanoseconds between the zeros and ones, 40 nanoseconds. So after transmission, we will have 10 nanosecond more from the rising part and 10 nanosecond more from the falling part. So we'll have such a signal on the output. So one will be observing in the middle, of course, it will be still 40 nanoseconds, but the edges of such a signal, they will be 10 nanosecond long rising and falling edge. It will be, yeah. So if we try to transfer the signal which has only 20 nanoseconds per bit, all the information will be overlapped. Yeah, this consecutive bits, they will be overlapping to each other, so that the transmission cannot be done with such a parameters. So it also gives some, let's say, bandwidth, maximum bandwidth of such a fiber, 50 megahertz per kilometer. at first approach, we can just tell it is 50 megabits per kilometer, 50 megabits at our modern time. This is nothing, in fact, yeah. Long time ago, 50 megabits per second, it was quite high transmission ratio, but for present days, it is pretty small, and it is per kilometer. It means 2 kilometer long fiber will have only 25 megahertz bandwidth. 10 kilometer long fiber will have only 5 megahertz bandwidth. Yeah, so you can see regarding our somebody just put no. I'm just answering the question asked on the chat. The pulse, I mean, this is the time of one single bit. Yeah, of course, ones will have some high value of the light intensity, zeros will have some small zero intensity of the light, but bit time is always the same. Yeah, so if you will have pulse broadening 20 nanoseconds and the bit distance also 20 nanoseconds, all the information will be overlapped. I mean, one bit will completely overlap another bit. And of course, it will happen all the time. Yeah, so I don't mean the bit is transmitted as a Dirac delta, for example. Only square wave with let's say 50% of the duty cycle, something like that. And this broadening acts more or less like increasing the rise and fall time of this square wave we are transmitting. It works like that. And you can see regarding these numbers I showed you, this type of a fiber is useless regarding our modern transmission rates needed by us. Even to one single let's say person, it is not enough, because right now we can have even 1 gigabit per second at home on the wall. So 50 megahertz, 50 megabits, it would be useless, in fact, for us right now. Yeah, even cell phone has much higher transmission rate available right now. So how to solve this problem? The first approach was to prepare a special type of the fiber, also with quite high core diameter, but refractive index of a core isn't step type anymore, but this refractive index profile is made with some special profile. It is more or less parabolic, and equation giving you this profile in a core is given here. Yeah, so as you can see, it is some type of square function having such a structure, such a refractive index profile. You can imagine what will happen. In the center of a core, the refractive index is the highest, yeah? So please remember, the refractive index means the velocity of the light beam. So all the rays which are traveling directly along the axis of the fiber, they will have the shorter, of course, geometrical path, but they will go through the media which has the highest refractive index, which means they are traveling at the slowest speed. Yeah, such a fiber, the propagation of the beam in such a fiber, of the rays in such a fiber, looks more or less like that, because this not constant refractive index in a core means also the beams, the rays, aren't traveling in straight ways, but they are bending through this gradient of this refractive index. Yeah? If you have gradient of refractive index, the ray is bended. It is traveling like on some curves, not traveling by using, let's say, straight lines, but it is bended. The whole path of the ray is bended in such a structure. And look, this ray, which is traveling along the axis of the fiber, as I told you, has the smallest geometrical path to travel, but at the same time, it just travels through the media which has the highest refractive index, which means it is traveling slower than the rays which are traveling close to this cladding. Yeah, this profile is chosen in such a special way that every of such a rays, this average velocity of the ray traveling through such a structure is exactly the same. So it doesn't matter which ray we choose, the time to fly through our structure will be exactly the same for every ray which is propagating through such a fiber. It is so-called graded index fiber, because this refractive index profile in a core, it isn't constant, but we have some gradient of this refractive index in a core. And in ideal case, of course, we should not have any difference between the times for every ray we have here. But of course, in real life, this refractive index profile isn't matching ideally this let's say mathematical formula I gave to you. So every difference between this ideal and real fabricated one will give us some slight difference in propagation time, but these differences can be much smaller than in typical step index fiber. As you can see, for modern graded index fiber, the bandwidth can be up to 10 gigahertz per kilometer. So it is way higher than for the standard step index fibers. So 10 gigahertz per kilometer makes this fiber to be good fibers for using at this, let's say, last mile of providing the internet to the home, for example. Yeah, they can be used in some local networks because the bandwidth 10 gigahertz per kilometer is pretty enough for such applications. But of course, for long distance transmission, it is also not enough, this bandwidth, because if we just want to transmit the signal at 100 kilometer distance, we'll have the bandwidth only 0.1 gigahertz for using such a fiber. Yeah, so 100 megabits per second will be available for such a long distance transmission through such a fiber. So as I told you, it is good for short distance communication, optical communication, but for long distance communication, such a high dispersion introduced by this kind of a fiber is also too big. Yeah, so we need to find, maybe not we, because it was found already, but there is there any way to just avoid these problems with different rays and other things appearing in such a structures? Of course it is. Yeah, if we just simply find a way to make a fiber which is able to transmit only one ray inside of it, we'll have no modal dispersion. I forgot to tell you this. All this broadening of the pulses in such a structure, it is so-called modal dispersion. Modal dispersion because every ray has different time of the propagation, so it leads to it goes to dispersion of the pulse, broadening the pulse. So it is so-called modal dispersion. And every ray propagating in such a fiber, it can be called as a mode. Different mode of the light propagating in such a fiber. So if we just simply construct a fiber which is able to propagate only one mode, only one such array, we should just completely zero this modal dispersion, because only one ray will be propagated, yeah, in such a structure. And how it is possible? It is possible if we just go with the sizes of this our core of a fiber close to the wavelength of the beam propagating in such a structure. In such a situation, we cannot use ray tracing to, let's say, describe the propagation of the light in such a structure anymore. Yeah. So of course, for big core diameter, we can use these rays to analyze the propagation of the light in such a structure, these reflections and so on. But if we just start to decrease the diameter of our core to, let's say, 10 microns, of course, you can imagine we should also be able to put the rays inside of it. But in fact, we should change the approach of our calculations here, because most of you already know the phenomena connected with the wave nature of the light beam, mainly the diffraction, for example. Yeah, closing with the object to the wavelength, I mean closing with the size of the object to the wavelength, makes all the wave properties of the light beam start to appear. So describing the light propagating in such a small structure needs to use wave optics instead of ray tracing optics and all the calculations. So to calculate such a beam propagation, we need to use not the ray tracing, but calculating some diffractive integrals and so on. Of course, we don't need to calculate it here on this lecture, but we are taking such a structure, refractive indexes, and we are taking electromagnetical field inside of such a structure using some Maxwell equation to calculate the distribution of the electromagnetical field in such a structure. And this leads to some, of course, solution for such an equation, giving you different distributions of the light intensity on the output from such a structure. Yeah, so you can see, for example, different angles of the propagation will give you different distribution of the electromagnetical field on the output from such a fiber. Yeah, so completely different picture than rays. Yeah, they are looking more like some dots or something like that. And you can also see this thing I already told you, this evanescence field. Every mode propagating in a fiber, some part of this mode is propagating also through the cladding of a fiber. Depending on the size of this core of a fiber, numerical aperture and other parameters, we'll have different parts of this mode field propagating also through cladding of a fiber. But decreasing the size of a fiber allows us to make such a structure which allows to propagate only such a electromagnetical field profile. Only one single mode. So it means the fiber will propagate only one mode. And this will be called, it is called single mode fiber. To calculate, to count the condition needed to have single mode fiber, there is some certain value introduced called normalized frequency. It is connected with some propagating constant of the electromagnetical wave propagating in a fiber. Once more, I don't want to show you all the equation needed to just derive all the formulas connected with these modal properties of the light traveling through the fibers, but all the solutions will give you such a result. This normalized frequency As you can see, it is dependent on the diameter of the core of a fiber, wavelength of the propagating wave in a fiber, and this factor. Do you know what this factor is? Do you remember? N1 and N2, these are core and cladding refractive indexes. This is the difference between them and square root of them. So this is exactly what's going on here. Equal to numerical aperture of the fiber. So we can also put this normalized frequency is pi, diameter of the core of a fiber, wavelength, and numerical aperture. What next? After calculation of this normalized frequency, we can also prepare a so-called curve showing you the propagation of such a different modes, and you can see here we have the first order mode, the mode I showed you, this one single dot, second order mode, third order mode, and you can see this second order mode can be propagated with the normalized frequencies higher than 2.405. This is the magical number. If the calculations will give you this normalized frequency lower than 2.405, it means the fiber will be able to propagate only this one single mode. Other modes cannot be propagated in such a structure. It means it will be single mode fiber. This is the name of it, and this magical number, nobody knows why this magical number is like that. It isn't equal E, it isn't equal pi, it isn't equal pi multiplied by something, it isn't equal or compared to electron, let's say, charge and other physical constant, but for the fiber, this condition for a single mode fiber is equal to 2.405. Nobody knows why this number is like that. Typically, you can imagine it is something connected with the pi or other constants, but here it isn't. So it is, let's say, quite interesting quest of the universe, in fact. Okay, so let's go further, just to remember what are the factors which are determining the fiber is single mode or not. As you can see, the wavelength, for example, increasing the to have a fiber single mode for one wavelength, it doesn't mean the shorter wavelengths will also be transferred in single mode way in such a fiber. So it is connected with some kind so-called cutoff wavelength for a fiber. It means the wavelength which is critical regarding this single mode transmission. Longer wavelength will be transmitted through such a fiber in single mode regime. The shorter wavelengths, they will appear as a couple modes of propagating through such a fiber, and it is quite easily visible for you in the laboratory exercise number, I don't remember, 2, I guess, semiconductor lasers. This red semiconductor laser, which is connected with the fiber, the output beam, if you just observe this output beam, it isn't ideally circular, but the shape of this output beam is changing because the red light isn't propagating in single mode way in the fiber which is connected over there. This fiber connected in this exercise to the output of the laser is single mode fiber, but for telecommunication wavelength, I mean for 1.3 micron and longer waves. But for red light, it is couple mode fiber. Yeah, so you can observe and see what's happening and how the output beam looks like if we have couple mode propagation in this fiber. If you want to observe some ideal pictures showing you different modes, different orders of modes propagating in such a circular fiber, I mean cylindrical fiber, the pictures looks more or less like that. We have two numbers. One number gives you the amount of the circles visible, yeah, and the second number gives you amount of the dots visible if we just simply move around the center of this mode field. Yeah, so increasing the mode number, will have more and more dots visible. This is ideal situation. Of course, in the real life, the modes are mixing with each other. So this mode field picture on the output from the fiber is much more complex, because if we just simply mix these modes here and additionally consider different phases between them, so we can have, for example, such a different picture like this one on the output of the fiber. Yeah, because if we just simply mix this mode and this mode, we won't have some, let's say, elliptical, but we need to just also consider phase differences between this mode and this one, because we will have some interference between them. Yeah, so the shapes will be completely different for couple modes propagating at the same time in a fiber. Okay, and typical construction of such a single mode fiber is exactly the same like step index fiber. The only difference is this core diameter. Typical for telecommunication fiber is 7 micron, so much smaller, as you can see. For these multi-mode fibers, we had 50 microns or 62.5 microns. Here we have 7 micrometers of core diameter. Of course, the condition necessary to guide a light through such a structure, I mean, higher refractive index for a core than for cladding, is also necessary here for such a fiber. And this fiber acts like propagating only one ray along the axis of a fiber. If we look closer, we'll see some light intensity distribution in the cross section of the fiber. So some part of the light, as I told you, is propagating as a so-called evanescence field in the cladding. Most of the light typically is propagating in the core of a fiber. And of course, if we just simply bend a fiber, this mode field will follow this bent core. So the beam will be propagating exactly the same way like the core of a fiber is bent. Yeah. So there is no modal dispersion in such a structure. So we have no limit at the maximum transmission rate, at least for now. And the beam propagating in such a structure and beam going outside such a fiber is almost Gaussian. Almost, because of this small difference in refractive indexes of a core and the cladding. So the profile of this is almost Gaussian. So you can treat the output beam from single mode fiber as a Gaussian beam, exactly the same beam quality. This perfect beam quality, you know already almost all about the beam, laser beams. So you know also what are the advantages of the Gaussian beams over the others types. And quick summary of these three main types of fibers: multi-mode step index fiber, huge modal dispersion, so very big broadening of the pulse, very low bandwidth of such a fiber; graded index fiber, multi-mode fiber still, but with very much smaller modal dispersion. So the rays are propagating in some curves in such a structure. Of course, the pulse broadening appears also, but the factor for it is much smaller. And finally, single mode fiber. So right now we know that we have no dispersion at all. So the pulse introduced to such a fiber, it isn't broadened in any way at least right now for today's lecture. Yeah? Of course, such a fibers also has some limits, but for now you can treat them as an ideal media to just transmit some signals. Okay, so limits about the maximum transmission rates. Right now we can just leave them for a moment. So we can go to other limits regarding this maximum distance of the transmission. And they are mainly because losses in optical fibers. There are a couple of the mechanisms of losses. Some of them we are able to just minimize, but some of them, unfortunately, not. And this one, which cannot be minimized, is so-called Rayleigh scattering. Also, absorption at some way can be minimized, but some part of the absorption cannot be minimized because it is given by the nature. Micro and macro fiber bending, these are the losses introduced by the fiber, not ideality the shape of the fiber. So of course developing the technology of making the fibers allows us to minimize also these factors. And last factor which introduce the losses in optical fibers are nonlinear effects. They can be avoided quite easily transmitting low optical powers, because nonlinear effects appears at high optical power levels propagating in the optical fibers. Yeah. So speaking about the fiber attenuation, at first we will speak and I will say a couple words about the absorption, because this was the main factor which was limiting the development of the optical fibers. You can imagine that the first optical fiber, which was made of glass, has losses close to 1000 decibels per kilometer. Does anybody of you has idea how high attenuation it is? If we want to express it using, let's say, our linear numbers. It is equal to 10 to the power of 100. Just to give you the idea how extremely high the number is, I can tell you that up to the moment right now, every star in our universe together just emitted 4 multiplied by 10 to the 84 photons. Yeah, so this is the amount of the photons emitted from the Big Bang until now. So if we just took all the photons emitted from the start of our universe until now and put through such a fiber, we can be sure that all of them will be lost, and none of them will go to the second side of our fiber. Extremely huge attenuation. It also means that 1 meter of such a fiber will attenuate 1 dB. Yeah, 10 meters will give us 10 dB of attenuation. 10 dB means 10 times. Yeah, so only 10 meters of such a fiber will transmit only 10% of the power put it to the input of such a fiber. Yeah, so this should just tell you how difficult the start of the fiber developing was, and main problem in making, let's say, fibers which don't have such a high attenuation is the purity of the transmission media. typically the glass, because the fibers, you know, I think already, typically, especially telecommunication fibers, they are made of glass. Of course, not the glass used for our windows. These are different types of glass. This is for the fibers. We are using extremely high purity silica glass. Silica glass means it is pure SiO2. Yeah, our glass in window has more additions, more dopants, so it isn't pure silica. For the fibers, almost pure silica glass is used. And as a start of, let's say, modern optical fibers, the year of 1970s could be taken, because in this year Corning just presented the fiber which has attenuation below 20 dB per kilometer. 20 dB per kilometer. Right now, of course, the standard is much higher, because modern fibers has 0.2, 0.3 dB per kilometers of attenuation at some certain wavelength. I will show you in a moment the wavelength for this certain low loss transmission. But I think the good point for this moment will be also to make you slightly more familiar with these decibels. Yeah, so could you tell me, for example, 20 dB of attenuation? What is the attenuation in our linear numbers? How many times the light is attenuated if we just attenuate a light with 20 dB?
A 100 times?
100 times, yeah. It is, in fact, quite easy to calculate if you know the formulas. Especially tens of dBs are easy to estimate, because every 10 of dB means 10 to the to calculate the linear gain or loss, yeah, gain or loss. This 10 to the amount of the dBs divided by 10. So 30 dB means 10 to the third. Minus 30 dB means 10 to the minus third. So it is 1,000 times less, and so on. Also, in optics, very often you can just meet optical power expressed in so-called dBms. This is the unit which is taken. It is some mix between the decibels and the linear power, and this is in reference to 1 milliwatt. So 1 milliwatt, this is 0 dBms of a power. 20 dBms will be 100 times more than 1 milliwatt, so it is 100 milliwatts, and so on. Yeah, so quite easy to calculate. So as you can see, tens of dBs is pretty simple to calculate, but in dB there is another magic number, easy to calculate and allowing us to calculate much more in decibels. Does anybody knows this second magic number in
3
the
dB.
3 dB? What is 3 dB in linear scale?
2 times.
2 times, exactly. It is 2 times. So it quite easily, thanks to this, we can easily calculate also, for example, 13 dBs. How many times it will be in linear scale?
20 times more.
20 times more, because we are using the main advantage of the dBs. It was invented just to help to calculate something, because calculating in dBs allows us to change some multiplication into some adding two values. Yeah, so 13 dB, it is equal to 10 dB plus 3 dB. So in linear scale, it is equal to 10 multiplied by 2. So it is 20. So 6 dB will be What value?
Four times.
4 times. 2 multiplied by 2. 9 dB.
Eight.
8. 2 multiplied by 2 multiplied by 2, yeah, but because it is 3 plus 3 plus 3. So look, knowing the properties allows you to quite easily calculate. So slightly harder example, 7 dB. Who can calculate 7 dB? What is in linear scale?
5 times.
5 times. How did you calculate it?
It's 10 minus 3, so 10 over 2.
Exactly.
Divided
To show other people. It is 10 dB minus 3 dB. So it is equal 10 divided by a 2. So it is 5, yeah? Exactly the same, 4 dB. This will be 7 dB minus 3 dB. So it will be 5 divided by 2. So it will be 2.5, yeah? 1 dB, it will give us 1.25. So you can see almost every unit dB can be easily calculated only knowing these properties of the dBs. And of course, since we know 7 dB, we can easily tell also what will be 27 dBms. What is the power? 27 dBms. How many watts it is?
500, so
500
half watt.
milliwatts, yeah, so half of a watt,
okay.
exact. So you can see, just making couple calculations using these dBs in such a way allows us to quite easy use these dBs to calculate different things, and in fact to calculate everything much easier way than using linear scale, especially regarding optical fibers. Because in optical fibers, typical optical transmission line has a lot of elements connected in one series, yeah. And designing such a transmission line, we need to calculate, for example, the attenuation of whole line. If we have all the losses, all the attenuations expressed in dBs, we can just simply add them together, and we will have attenuation given by a whole transmission line. If we will have linear transmission, linear attenuation given by every element in our transmission line, we will need to multiply them together. It will give quite complicated result, in fact, because, for example, transmission of a connector can be 0.9 multiplied by transmission of the fiber 0.5 multiplied by transmission of a splice 0.95 and so on, yeah? So you can see this kind of calculations are much more difficult, and the mistake can be made much easier for such approach to calculate anything in this optical designing. So this is why we are using dBs and also dBms, because having power expressed in dBms and having loss or gain expressed in dBs quite easy allows us to calculate the powers after some loss, after some gain, and so on, yeah? Because we are only subtracting or adding values together. And right now I'm presenting you typical spectral attenuation of a fiber, typical silica fiber. It is modern fiber, yeah? So as I told you, for certain wavelength, here we'll have some minimum transmission, and you can see also all the components of the attenuation for different wavelengths. The Rayleigh scattering, as I told you, this is the factor which cannot be avoided, because it is scattering on the this nano uniformity of the material, on the particles of the material, in fact. So we cannot have the fiber without any particles of the glass, yeah? So since we have a glass, the glass is made of particles, the particles are scattering the light. And unfortunately, this scattering is extremely dependent on the wavelength. You can see this this chart starting from 0.7 microns. So the visible light is somewhere on the left. And here you can see why we aren't using visible radiation to transmit through optical fibers. You can imagine it increases significantly in this visible domain. And for blue light, the attenuation of a fiber will be extremely high. So they aren't practical in any way. And as I told you, it is physical limit. So we cannot avoid it in any possible way. So this is why all the telecommunication through optical fibers is made in infrared wavelength. Yeah. Another component which cannot be avoided is this ultraviolet absorption tail. So it means also for ultraviolet, we cannot have optical fibers almost at all, because for such a short wavelength, the absorption of the glass is extremely high. But we have also limiting factor on the right, this infrared absorption tail, and this is absorption given by the particles of a glass, as I mean this SiO2 particles. They have some vibration, rotation energy levels, so they are absorbing some certain energy photons, and since they are made in some solid state structure, the absorption lines becomes bandwidth. So let's say after 2.2 microns, typical silica glass is completely absorbing also such a wavelength. Yeah, so you can see we have, let's say, some physical minimum of our spectral transmission of a fiber, and it is somewhere close to 1.5 micron. You can see also additional components of this absorption, this OH minus ions, these hydroxide ions. Could you just tell me where do these ions come from? How can appear in a glass? What are these hydroxide ions?
Or like from water?
Exactly. If we have a water particle, of course, we have so-called dissociation of the water into H plus ions and OH minus ion. So this is the water. Of course, it doesn't mean the glass is wet of water, but even small amount of the water particles built inside the structure gives huge absorption bands at this certain wavelength, and developing of the glass and this pure glass at some certain level started to be developing of the glass without any water inside of this glass. It is at some certain level, because we want to have zero water in a glass at all during the process. So developing of the pure glass for making the fibers at some certain point start to be fighting with water in whole process of making the glass. Before reaching this let's say threshold, these OH ions gave us something like that. Yeah, this absorption of a fiber with a lot of water built inside of a glass was this whole shape was something like that. Yeah, so for this longer wavelength, the fibers also had huge attenuation. So developing a fiber and developing from the second side, developing the light sources these were some, let's say, milestones of developing telecommunication systems and so-called optical windows connected with these systems. So first telecommunication window at the wavelength of, you can see, let's go back. You can see 850 nanometers. This was, in fact, you can see first or almost first semiconductor laser was operating near to this wavelength. Yeah, so it was pretty easy to fabricate the laser which is operating at 850, and from second side, the characteristic of fibers were more or less like that for that times. Yeah, so this is why they choose to operate with these first generation systems at this certain wavelength, because longer wavelength weren't possible regarding the attenuation of the fiber, but also availability of the sources, because lasers used for the telecommunication, not only the lasers, but also light emitting diodes, I mean semiconductor light sources, because only this type of sources is easy to just couple with the fiber, to put the light from such a source into the fiber. You can imagine we have extremely small core size, so if we want to put reasonable amount of the light into such a fiber, we need to have also source which is able to emit, let's say, well-defined, nice quality beam to put inside of the fiber. So there was also development of the sources, yeah, starting from gallium arsenide lasers and some modifications, some different components added, but with such a, let's say, amounts of the gallium and indium, for example. So after some certain time, they developed such lasers operating in this wavelength, yeah, and also detectors. This is another story. Detector also need to use some certain semiconductor for operating and some at certain wavelength. Of course, it just came with operation to this. Yeah, so the fibers were available to also have minimum losses at 1.3 micron, and finally, this was developed not so long time ago, 20 or 25 years ago. Finally, the technology of the semiconductors allows to make the sources for such a wavelength, and this technology of making the fibers allows to making pure modern fibers with low attenuation at this minimum possible attenuation 0.2 decibels per kilometer. Yeah, so this was the last stage of the fiber developing regarding these losses introduced by the fiber, and we cannot expect we will have another step, because physics is forbidding us to have lower attenuation than this 0.2, 0.18. These are the physical limits. So right now the technology hits the physical limits, in fact, regarding this attenuation introduced by a fiber. And because, you know, the sources are available even for 2 micron wavelength and even longer wavelength, but unfortunately the minimum absorption for silica fiber is at exactly 1.5 micron. You can tell maybe there will be some new glass developed for transmission and longer wavelength, and maybe after, let's say, couple tens of years, maybe they will develop something else better for this longer wavelength or with lower transmission. But right now there is no sign to this to happen. So right now you can almost with 100% say we are at the limits of the physics with this optical fiber attenuation and the wavelength which are available for us to transmit the data at long distance. Okay, So I think it's enough for today. I'm over 5 minutes than normal time. So of course, if you have questions connected with this lecture, it's a good time to ask.
I have one connected with critical angle. So the minimum bending radius of the fiber is more connected with this critical angle or like mechanical strength?
Exactly, minimum bending is that it depends, because if you look, I think you are speaking about some data sheet for the fiber.
I mean, I remember there's some rules about the bending of the fiber.
Okay, so if you are speaking about the rules, yeah, these rules go strictly from this critical angle given by these refractive indexes, because it is the radius which guarantees you no losses introduced by such a bending. Yeah, if you bend the fiber with smaller radius, the lights will start to go outside the fiber. But in the data sheet of a fiber, sometimes another bending radius appears, so-called short time bending radius, and this is the mechanical, given by the mechanical properties of the fiber. So this bending radius is much smaller, of course, but it does not guarantee you no losses at such a bending, only not destroying the fiber if you just simply bend the fiber with such a small radius.
Okay, thank you.
Okay, so thanks for today. If you don't have any more questions, so see you on Monday on the laboratory, in fact, and of course on another lecture in a week time. So goodbye.
Thank you. Goodbye.
Goodbye.
Goodbye.